Okay, so today we're diving into something pretty complex but super fascinating.
Yeah.
Quantum computing.
Right. Yeah.
We'll be exploring this document called
Ah.
Exploring the Fascinating World of Quantum Computing,
All right.
how qubits, entanglement, and interference are revolutionizing computation.
Wow.
Pretty dense title, I know.
Yeah.
But trust me, the ideas here are mind-blowing.
Okay.
So we're going way beyond the zeros and ones of our everyday computers.
Right.
Get ready for qubits, entanglement, and even something called quantum interference.
I'm ready.
And we'll try to make this intimidating topic a bit less, well, intimidating.
Yeah, it can be a little overwhelming.
And we'll really see what kind of real-world impact this could have.
That's the most important part, I think.
So let's start with the basics. How is quantum computing different from the computers we use every day?
Well, it all comes down to how information is processed at the most fundamental level.
Okay.
Classical computers, the ones we use every day, they use bits, and a bit can be either a 0 or a 1. Simple system, but it's built the digital world as we know it.
Right, the foundation of everything.
Exactly. But quantum computers, they use qubits.
Qubits.
Now, a qubit can be a 0, a 1, or both simultaneously.
Both at the same time.
Yes. And this both at once possibility, it's called superposition.
Superposition.
And that's where things start to get really, really interesting.
I have to admit, this idea of something being in two states at once, it's tough to wrap my head around.
Yeah, it's not very intuitive.
Not at all.
It kind of defies our everyday experience. But imagine, like, a coin.
Okay.
That can be both heads and tails at the same time.
Okay.
Until you look at it, you don't know which state it's in, but it
Right.
has the potential for both. That's a very, very simplified way to think about superposition.
So it's existing in all possible states until you observe it.
Exactly. And the real power comes when you have multiple qubits in superposition.
Okay.
They can actually explore all possible combinations simultaneously.
Oh.
So they can perform calculations in parallel at a speed that no classical computer can match.
Okay, so it's not just about the qubit being a 0 or 1. It's about this superposition that unlocks this massive processing power. I think I'm starting to get it.
It is a pretty wild concept.
It really is.
Yeah.
But what about this entanglement thing?
Yeah.
It sounds a bit like science fiction, honestly.
Well, entanglement is where two qubits become linked.
Linked.
Yeah. They become connected in a way that even if they're physically separated, they still influence each other.
Okay.
Think of them like a pair of dice that always roll the same number no matter how far apart they are. If you measure 1 and it lands on 3, you instantly know the other one is also a 3.
So it's not just that they're correlated, they're like fundamentally linked.
Yeah, exactly. It goes beyond ordinary correlation.
Okay.
It's a fundamental interdependence. Einstein famously called it spooky action at a distance.
Spooky action.
Yeah. And, it really challenges our classical understanding of cause and effect because the information seems to travel instantaneously.
Wow. It really does mess with your intuition about how things should work.
It does, yeah.
So we've got these qubits in superposition, entangled in this mind-boggling way.
Right.
But how do we actually use them for computation?
That's where quantum interference comes in.
Quantum interference.
Yeah. It's how we harness the strangeness of quantum mechanics to do actual computation.
Okay.
Think of it like waves in a pond.
Okay.
When two waves meet, they can either amplify each other, creating a larger wave, or they can cancel each other out.
Uh-huh.
Similarly, quantum states can interfere with each other, and by carefully manipulating this interference, we can actually guide the computation towards the desired result.
So it's like conducting a quantum orchestra.
Exactly. That's a great way to put it. Like we're orchestrating these quantum states to solve complex problems.
This is all getting a bit less mind-boggling and a lot more fascinating.
Glad to hear it.
But how does this translate into real-world applications?
Well, one really interesting example is Shor's algorithm.
Shor's algorithm.
Yeah. Now, this algorithm, running on a quantum computer, could factor large numbers exponentially faster than any classical computer.
Okay, and factoring large numbers, why is that important?
It has huge implications for cybersecurity. Much of our online security relies on the fact that it's very difficult for classical computers to factor large numbers.
So that difficulty is what keeps things secure.
Exactly. It's what keeps our online transactions and communications safe.
Right.
But Shor's algorithm on a powerful quantum computer could crack these codes wide open.
Potentially compromising sensitive data.
Exactly.
Wow, that's both exciting and a little bit terrifying.
Yeah, it definitely has both sides to it.
So are we on the verge of a quantum revolution? Are classical computers about to become obsolete?
Not quite. Quantum computing is still in its very early stages.
Okay.
There are significant technical challenges to overcome. Qubits are incredibly sensitive to their environment, and maintaining those delicate quantum states, it's difficult. We're also working on things like error correction and scalability. It's more likely that quantum computers will complement classical computers, not replace them.
Working together.
Yeah, think of them as specialized tools for tackling specific problems.
Okay.
Problems that classical computers struggle with, like drug discovery, materials science, and optimization problems.
So we've learned about superposition, entanglement, and interference. We've touched on the potential impact on fields like cybersecurity.
Right.
It's clear this technology is going to be a game changer,
It really is.
even if it's not going to replace our laptops just yet.
Not just yet.
What's truly remarkable is that we're using the strangeness of quantum mechanics to do actual computations.
It's quite amazing.
And we're really just at the beginning.
Yeah, the surface has just been scratched.
There's so much we're still discovering about the quantum world.
Absolutely.
And that brings me to a final thought for you all. If we're able to manipulate these quantum phenomena to break existing encryption, what new forms of security will we need to develop in this quantum future? It's definitely a question worth pondering as we continue to explore this revolutionary technology.
Absolutely. Something to think about.
Okay.